guys, Mr. Levine here again, Mr. M. And I was asked to do something on exposure, recorded exposure. I guess we had contrast, we had spatial resolution, we had distortion, but we didn't have exposure. So again, I'm gonna write this on the board. You have prime exposure factors, and you have image quality factors. So there's two different ones. So I want to make sure that you know that they're different. So image quality factors are different from prime exposure factors. Now, if you remember your prime exposure factors, you had MA, you had time, you had KVP, which are on the console, and then you had the distance, and your distance was your SID, correct? That's in your exam room. So they're different from image quality factors. Image quality factors, you have recorded IR exposure. It used to be, it's not synonymous, but we used to have what's called density. And density are the exposure levels, the blackness on the image. Then we have contrast. All right, we have contrast. And I'm gonna sneak in here, you guys, I'm gonna sneak contrast resolution in here as well. Okay, even though it's not one of the four, but I'll put that in here in parentheses. Then we have spatial resolution. And then we have distortion. So this is how you're gonna critique your image. You're gonna make sure that it has the right exposure. You're gonna look at your exposure index number. You're gonna make sure it has the right amount of grays, right? Your gray scale, your contrast. Make sure that you have the sharpness of the edges of the lines of the object that you want. And then you wanna make sure you don't have a lot of distortion, either size or shape. And there's some things we can't get away from, but that's, again, I love working in radiography because you got so many things working against you that you're trying to create something good out of it, right? So I like the challenge. But today, I'm gonna focus on recorded exposure, all right? So recorded exposure is the X-ray signal that goes through the part and hits the detector, correct? All right, so let's go ahead and do that again. So you have the object, you have X-rays coming down. Whatever goes through, that's exit radiation or remnant radiation. And you're gonna find that I repeat a lot of the terms because guess what? Repetition is key, right? So I'm gonna repeat a lot of these terms over and over again in different videos that we're gonna record for you. You're gonna have terms that are related again to the previous videos. So again, exit radiation, remnant radiation goes through, and now it's gonna hit your detector, right? It's gonna hit your IR. So this X-ray energy, these photons, are gonna be signal that's gonna be recorded and detected. And you have different types of receptors. We have TFTs, we have CCDs, we have CMOS systems. In the older systems, we have CR systems, we have PSP, right? So these are all the detectors that record the exposure. From there, it's sent to the computer for processing, correct? So today, we're gonna focus on what's gonna increase exposure. All right, so if you know what increases exposure, you're gonna know the opposite, what's gonna decrease exposure, correct? And again, you guys, I'm referring to chapter 26. I'm looking, there's a chart here on the page 365. I love the charts. Look at those charts. We're looking at the Carlton Allen textbook again. So if you have a different textbook, maybe a Bouchon or something, you guys, again, there's gonna be something at the end of the chapter that tells you exactly what's happening. All right, so page 365 for you guys in here. Now, if you increase your mass, you're gonna have an increase of recorded IR exposure. So remember that your digital systems have a linear response to the exposure. If you go up in mass, you're gonna have a greater quantity of X-rays reaching the IR, right? If you go up in MA is part of mass, correct? If you make your time longer, you go up in time. All of this is gonna increase your exposure because you're increasing either the quantity, okay, or the length of exposure. So if you do any of these two things, you're gonna go ahead and increase the amount of exposure recorded by the receptor, correct? Now, the other item is gonna be KVP. KVP is the punching power, the pushing power of the X-ray. It's the energy behind the photon, correct? So if you increase KVP, all right? And I say KVP, I'm old, right? But it's gonna be KV now. But I still say KVP, right? But KV, kilovoltage, right? Peak power. If you increase it, you're going to increase IR exposure. But I want you to know the why. All right? In my classes, we always say, okay, we understand the answer, but why? Right? We know that's the answer, but why? If you follow with the why, you understand it, it doesn't matter how they word the question. When you take the ART exam, when you're taking your exams in class, it doesn't matter how they word the question. You understand the why behind it. You can answer it in any way or fashion that they ask you, correct? So, increasing KVP, I'm going to give you guys an example here. Let's say you go from 60 kV to, let's say, 70 kV. Right? So, let me draw this. Okay, now what do you see? A difference in my wavelength, correct? So as you increase KVP, the wavelength becomes shorter, correct? You're going to have a higher intense energy. The frequency is going to be higher, right? So as you increase KVP, the wavelength becomes shorter. That's inversely related, right? As you lower the KVP, the wavelength is longer, right? So the longer the wavelength, the less intense. So if we had some photons, remember photons are a bundle of energy that travel in wave, and you x-ray this body part, let's say you only have 2 x-rays hit the detector, and now we have 2 recorded exposure levels. This is all hypothetical, of course. This is not going to be equal to the amount that we're using. Let's say you have 70 kVp, you're going to have twice the amount of x-rays go through. So that means you're going to have twice the amount of recorded exposure levels. You're going to have more densities, correct? So we need to understand, as you increase KVP, let's say for example 60, 70, the wavelength of the energy is going to increase, the intensity is going to push through more x-rays. That means more x-rays are going to hit the detector, and that's going to increase IR exposure, okay? Now, that's KVP. So notice we have MA, time, mass, we have KVP. What's the other prime exposure factor that we said, but not on your console? It's in the exam room. It's going to be your SID, correct? So the SID has an inverse relationship with exposure. So as you decrease SID, you're going to increase IR exposure. So let's draw this out. Let's say we're at 72 inches SID. Here's your X-ray tube. Here's your IR. Now let's say we cut it in half. So let's say we go to 36 inches SID. So now, when you decrease the distance, let's say we have this amount of exposure hitting the detector, hitting the receptor, but when you cut the distance in half, or even if you just decrease the distance, what happens to the intensity of the energy? It's going to go up. One of the analogies is the flashlight, right? You bring a flashlight, or even a flame, right? You put your hand close to the flame, it's going to get hotter. The intensity is hotter. Don't try this at home, right? So as you bring your hand away, it's going to get cooler, right? Because the intensity of the energy decreases over distance. So let's say here now, so now you're going to have 4 times the recorded exposure. So as you decrease the distance, your SID, the intensity of energy increases, and you're going to increase the receptor exposure. Does that make sense? All right, so I'm kind of just applying the inverse square law here for you, just sneaking in there a little bit. But as you decrease the distance, let's write this down. As you decrease your SID, your intensity of energy is going to increase. And when you have an increase of intensity, you're going to have an increase of image receptor exposure. Okay, all right. Now, these were the prime exposure factors. But there's other factors that are going to influence your density exposure as well. And they're going to be maybe the generation of the system, right? A high frequency system compared to a single phase system is going to be totally different. There's always, you guys, always an old X-ray room that nobody wants to use, and that's when they always give you students to use, right? And the techs are all grabbing the newer room, right? So the older room, let's say, is a single phase 2-pulse X-ray generating system, and you are given permission to use the new system now, right? So now you want to go from a single phase system, and you want to go to a high frequency X-ray generating system. Well, if you do that, you got a half the mass. You can go ahead and multiply it by 0.5, or you could divide it by 2. But you're gonna half the mass because you're gonna get more x-rays out of a high frequency x-ray generating system. So when you have a high frequency x-ray generating system, you get more pulses. More pulses are gonna be more x-rays. More x-rays means more exposure again. But what if now they put you back in that old room and now you go and you have to take an x-ray, let's say a hand, and in this system you maybe used, let's say, I don't know, I'm just gonna make up a number, 1.6 mass in the high frequency. In the old school system, the single phase, you have to use 3 mass, 3.2 mass for a hand. I'm just making up numbers here. So you're gonna have to double your exposure. So you would have to double the mass, all right? So you're gonna have to double your mass to use it on an older system. So this is what I want you to know. When you use a high frequency x-ray generator, it's gonna increase your IR exposure. Because when you increase the number of pulses, you're gonna have more x-ray quantity. When you increase the x-ray quantity, you're gonna get more IR exposure. Okay? So you don't have control of this. This is designing the system. All right, so again, if you got all brand new systems, then good for you. But if you don't, you're working at a smaller hospital, community-based hospital, they don't have the budget for that, there's always gonna be an older unit in that area. You can have 4 or 5 x-ray rooms, correct? And one of them might be an old single-phase unit system that you might have to use, okay? So, it can be done, right? Now, the other item here is gonna be filtration. So filtration is also set. But if you decrease filtration, that's gonna go ahead and increase your IR exposure. Now, again, we don't change filtration. Back in the days, we had to change the half value layers, you guys. That's how old I am. But we had to slide this piece of aluminum out between the collimator and the x-ray tube. But we'd have to slide this piece of aluminum out. But we don't have to do that anymore. But filtration, if you go down in filtration for whatever reason, it's going to increase your IR exposure. Okay? Collimation. If you decrease collimation, this always gets people. If you decrease collimation, that means you use a larger field of view. Okay, so if you increase your collimation, that means you're making the field smaller. This is what gets people. But if you decrease collimation, that means you're not using much of it. You're opening up the field of exposure. So if you go from, let's say, an 8x10 field of exposure, and now you go to a 14x17 field of exposure, you're not decreasing it, right? You're opening it up. You're gonna have more x-rays strike the detector in your field of view compared to 8x10 here. So again, when you decrease collimation, you use a larger field of view, you're gonna have more receptor exposure. Does that make sense? Okay. So again, be careful with the wording here. The next one here is gonna be part thickness. So part thickness. When you decrease part thickness, you're gonna have an increase of IR exposure. So let's give you an example. You go from, let's say, 10 centimeters to 4 centimeters now. And you use the same technique, you're gonna have an increase of x-rays going through the object. Okay, so let's say you only had 2 here and you had twice the amount of exposure going through. So when the part thickness decreases and you don't change the technique, same, you're gonna have an increase of IR exposure. Well, even if you have a change in technique, you're still gonna have more IR exposure recorded because the part is smaller. So think about it this way. If you're doing my arm, okay, this is my humerus, my arm, versus a pediatric, an infant arm, right? Which one's gonna have more IR exposure? The pediatric infant arm, correct? So again, you're gonna have to decrease because you're gonna get more x-rays going through a smaller body part. Does that make sense? All right, now the next one is, let's go part density. Part density. So the density of the object. So if you decrease the density of the object, you're going to have an increase of IR exposure. So let's give you an example for that. So let's say you have, oh, I got a good one here for you. Let's say you have a patient that has more muscle. More muscle is more dense, right? You're going to have a lot of the radiation be attenuated by the muscle, correct? But if you get a patient that doesn't have a lot of muscle, the X-rays are going to go through that object, right? It's going to be more radiolucent. So as the atomic density decreases, you're going to have more IR exposure. Does that make sense? Okay, because it's going to go through the object. The higher the atomic density, it's going to have more photoelectric effect. You're going to have more attenuation, right? It's going to be radiopaque. The X-rays aren't going to go through it as much. But if you have an object that doesn't have a lot of muscle, let's say it's a little bit more adipose tissue, it's going to go right through it, create more scatter too, right? So, but your IR exposure is going to go up when the atomic density is changing. All right, I'm trying to go down to this list here. The next one is pathologies. So right now we're just focused on increasing IR exposure. So if you have a destructive pathology, so destructive pathology, we have a separate little video on destructive pathologies. Destructive pathologies have a loss of density, all right? They have a loss of tissue density, or they have more air. Now that becomes more radiolucent. So if we have an object that's more radiolucent, X-rays are going to go right through it more, correct? So destructive pathologies, more radiolucent pathology type diseases, you're going to have an increase of IR exposure. Let's talk about a couple of them. What's one that you have in the lungs where you have a hyperinflation of the lungs, an irreversible dilation of the alveoli, you have blunt edges of the lungs, right? A flattened out diaphragm, right? It's going to be, starts with an E, okay? You got an emphysema, okay? So I saw one person get it. All right, so emphysema. So emphysema, your lungs hyperinflate with air. And what do we say? It's going to become more radiolucent. That means X-rays are going to go right through it, right? Another one is osteoporosis. That's another common one. So osteoporosis is where you have a decrease in the atomic density of the object, right? Because you have less bone markings within the bone itself, correct? So when you have a destructive pathology, you're going to have more IR exposure. Okay? All right. Now, I'm going to add grids. So grids are used to attenuate scatter before reaching the IR, correct? But, okay, no grid is going to increase IR exposure. No grid is going to increase IR exposure. So if you have an object and you add a grid, what's the grid going to do? It's going to attenuate some of the radiation, correct? That's why you have to go up to compensate when you use a grid. But let's say you take away the grid now. All right, you take away the grid, now you don't have that device to attenuate the radiation. So now you're going to increase your IR exposure by not using a grid. All right. Now we're not asking the question, you know, is it the size of the patient, what kind of KV we have. We're just saying if you take away the grid, you're going to increase IR exposure. I was talking to one of my students about this yesterday, and she's getting ready to take her ART exam, and she was saying, oh my gosh, Mr. Aram, you know what, I tend to overanalyze things. And I said, do you read the question and start asking yourself, is there a grid? Does the patient have diabetes? You know, do they have this? And she says, oh my gosh, I do. Just stick to what they're asking you, okay? Don't start adding your own twist on things, because you'll take that wrong answer in your head and you'll create it into a right answer, right? Just focus on what they're asking you in front of you. And you guys hear me say this, focus on the task at hand, just what's in front of you. Don't start deviating and thinking about other things. So again, don't start saying, hey, does the patient, are they obese? Are we using a high KV? What procedure are we doing? Stay away from that. Just focus on what they're asking you, okay? So we did the grid ratio. We don't have to do relative speed anymore because that's old school for film. We got filtration. We got the pulses. We got here mass. And we got filtration. So we pretty much have gone through that whole list. I know I did it kind of fast. I know that I did it kind of concise, but again, this is kind of just a brief overview, and I'm telling you, you study this, you guys, and it's gonna take you a long way. It's gonna just make you a better tech, a better radiographer. If you're studying for the ART exam, this is gonna help you, okay? All right, so you guys take care, bye-bye.